Hi everyone. This is in response to some of your questions for today's lecture on standard reduction potentials and using them to predict the direction of spontaneous change. In this equation that I worked through today, I had one question: is this reaction easily reversible? I don't know so much about the word easily, but it is reversible. In theory, any chemical reaction is reversible. And so the spontaneous change here is if I take a piece of copper and put it in a solution of silver nitrate, copper goes into solution and the silver comes out of solution as a solid. That's the spontaneous direction of change, but I can force the reaction to go the other way if I run a really strong electrical current through this. If you do that, then you're basically forcing the electrons to go in the opposite direction. So I would say it's reversible, but you need to supply a lot of external work, a lot of external energy to force it to go in the opposite direction. Just like you can force a non-spontaneous reaction, like the folding of a protein. You can get that to occur by expending some energy from another reaction, like the hydrolysis of ATP. So same basic idea, you can reverse this reaction, you just need to provide an outside source of free energy to do that. For this reaction, what is the equilibrium constant? Or rather, what's the law of mass action? What is the K value for this? Well, the K value should be the same thing that we would have expected for any chemical equation. We'll have products over reactants, so that's going to be the concentration of the copper times, or rather divided by the concentration of the silver ions squared. Leaving out the solids, we always just assume that they have unit concentration and then essentially leave them out of the law of mass action. Now, I will say, because I don't want to, like I said, this is the equilibrium constant that you would get if you're just looking at the equation. I will give people a preview of Wednesday's lecture, which is that there is a connection, there is a relationship between the cell potential and the equilibrium constant. So I'm not going to derive this for you, but I will tell you that there's generally a relationship between cell potential, how strongly, how favorable it is for this reaction to occur, that happens to be related to the equilibrium constant by the, well, technically it's actually the natural log of the equilibrium constant. And then there's a couple other prefactors here. It's like 0.0257. So this 0.0257 volts, that takes into account a couple of fundamental constants, and it's also assuming that this reaction is occurring at 298 Kelvin. So this has a couple of constants in it. That's where these voltages are coming from. This N here is the number of electrons transferred. So in this reaction, there happens to be 2 electrons transferred per mole of copper. Each copper donates 2 electrons. That's why it picks up the 2+ charge, and it donates those 2 electrons, one each of them, to the silver ion. So for this, I would just say, well, the E cell should be related to the natural log of the equilibrium constant by a factor of 2 there, or really, I guess, a factor of a half. Are certain ions more, okay, sorry, again, I will go into that expression in more detail on Wednesday, but your question was about the equilibrium constant, and I just wanted to assert that there is a connection between the material we discussed today and equilibrium constants, but how you actually get this we'll discuss on Wednesday. Are certain ions more likely to grab electrons than others, and if so, how does that affect the equilibrium constant? Yeah, some substances, some elements do just have a better tendency to grab electrons. We represent their tendency to grab electrons, to gain electrons, by their standard reduction potentials. So you saw that table that I presented. You can find a much larger table in your textbook in table 18.1. And yeah, we rank substances, we rank cations and metals for that metals and gases by their tendency to accept or grab or reduce themselves to grab electrons. So how does that affect the equilibrium constant? It affects the equilibrium constant because the cell potential in turn is going to be equal to the difference in the standard reduction potentials of the electrodes at the cathode and the anode. So again, these values here, these are my standard reduction potentials. This is the actual cell potential that I get, which you'll have after you connect these two electrodes. So how does that affect the equilibrium constant? Well, if you change out how badly things are accepting or donating electrons, you'll have a slightly different cell potential, which in turn means you'll have a slightly different equilibrium constant. The reaction will become slightly more favorable or slightly less favorable, depending upon what metals you substitute in or out. Along those lines, you mentioned that this reaction is favorable, but generally speaking, why would an element give up an electron? It's not so much that they want to give up electrons. Even taking an electron off of a sodium atom or a lithium atom, that requires an inflow of energy that doesn't just fall off. Otherwise, if that were the case, every time I had a chunk of sodium, it would automatically turn into sodium plus. So it's not so much that they really want to give up an electron, but they might be happy to give up an electron if there's something willing to take the electron. And so that is, again, how we are distinguishing between elements based upon their reduction potentials. How happily are they to take electrons versus how happy are they to give up their electrons. Something on average, if I have two species that both like to gain electrons, the electron will be transferred to whichever one wants to gain them more. And in doing so, then an electron is lost from one species but gained by another. So why would an element give up an electron? It would give up an electron if there's something there that will happily take it. So again, we don't normally think, we'll frequently write half reactions. I might write, for instance, this one here, the copper oxidation reaction. When it loses an electron, I can write it like this as a half reaction, but it usually doesn't just occur as a single half reaction. Normally there needs to be something else present to take those electrons and make the process favorable. I see a similarity between our discussion today with Newton's heat law, that if I have two substances and they have a large difference in temperature, I have a very large amount of heat flow between them. And similarly, if I have a large difference in cell potential, the reaction becomes more spontaneous. I can see that logic. I would say that, yeah, it does seem reasonable to say that there is an analogy there. The two processes are analogous in some way, but I wouldn't go too far with that. It's true that if I make the difference in temperature between two substances larger, when I put them in contact, I'll have more heat that flows in between. But the difference there is, let's say I let's say I don't make the difference in temperature larger. Let's say I make the masses larger. I make one material, not only is it hotter, but it's also significantly more massive. Then it also has more thermal energy to transfer. And in doing so, you'll have more heat transferred. There's not the same correspondence with standard reduction potentials. Just because you have twice as much material doesn't make the reaction twice as favorable. There's going to be twice as much energy released, but you would still need, twice as many other substances around to take the electron. So I think I mentioned this today, that you can double the amount of material, or you can double a reaction, but the cell potential or the standard reduction potential doesn't double with it. I'd say it's more reasonable to think about potential as being a difference in height rather than a difference in temperature. Now, Temperature itself is technically a thermodynamic potential, so I agree. There is a little bit of correspondence there, but I hazard to encourage people to think about that analogy too much. You said that electrons move towards higher electrical potential, but I thought that in general, objects tend to move towards lower potential energy, move to lower their potential energy. You're absolutely right, and I admit that that does seem to be counterintuitive. And the short answer is that it's because electrons are negatively charged. Formally, if you want to go into the physics of this, formally, electrostatic potential is defined as equal to the magnitude of some charge that is exerting an electrostatic potential divided by 4 pi epsilon naught. This is the permittivity of the universe, just a bunch of constants over the distance between them. So it's a potential in the sense that it depends upon where an electron is relative to this test charge. If I want to calculate, okay, that's just the potential. If I want to calculate potential energy, though, that is going to be equal to another charge times the potential that it's experiencing. So that's a subtle point here is this is the potential. And it tells you basically how much potential energy another charge, or rather I should say, the potential energy that another charge experiences is equal to the magnitude of that other charge times the potential. And the thing that makes this annoying here is that the charge on an electron is negative. So technically you pick up a negative sign here. So the larger your electrostatic potential, the lower your actual potential energy. So, like I said, it's annoying. I promise you that your instinct is right, that your instinct that things tend to move towards lower potential energy, that's true, but because of electrons' negative charge, it turns out that electrons moving towards higher potential actually lowers their potential energy, just again because of the opposite sign. Potential, again, was originally defined by Benjamin Franklin in terms of positive charges, even though we think of electrons as being the dominant charge carriers in any electrochemical reaction. He still defined it originally in terms of this positive charge, so we're stuck with this annoyance. But anyway, that's just something it's a tricky thing to just be aware of, that electrons move towards higher potential, period. And we do make a subtle distinction between potential and potential energy. So I discussed this a little bit in my 9-10 class, but I'll mention this for the 8 a.m. class if you would like to have a further discussion of like what's the difference. I discussed this, the potential energy that an object feels like. Suppose I had some ball that's in the middle of the air and it's a certain height above the ground. It experiences a force of gravity which is equal to its mass times the acceleration of gravity. Its potential energy should be its mass times gravity times its height. This would be its potential energy, and its potential, I would say, is analogous to the height. So just like the point being is we do make a subtle distinction between potential and potential energy. Potential is this general function that depends on position. Potential energy is how your energy depends on that potential, how your energy actually depends upon position. So it's one more step removed here, and that one removed step has a negative sign in there, and that's what solves the possible confusion, or actually creates possible confusion about electrons going towards higher potential, and in doing so going to lower their potential energy. Does the charge on an ion have any effect on its voltage? For example, silver plus, copper 2 plus, copper 3 plus. Generally, there's no real correspondence between the charge on an ion and its reduction potential. So, yeah, I will just say that generally there's no correspondence. Now, there may end up being some, but you know what? I'll just say that no, there is no correspondence between the charge of an ion and its voltage and its standard reduction potential. Is electrostatic potential, is cell potential, is that a state function? Can we use Hess's law? Yes, it is a state function. The potential, just like position, just like height, it is a state function. Doesn't matter how you got to a certain height, you're just now at that height, and now your height is whatever that height is. Any changes in height are just going to be your final height minus your initial height. We'll do the same thing with electrochemical potential. That the change in the cell potential is just your final state minus your initial state. If we think of the cathode as where the electrons are gained, that's where the electrons go to, that's where they end up. This is your final state. The anode would be your origin state. Where are the electrons coming from? So this is your final minus your initial, that's the cell potential. So we're using it the same way we would Hess's law. So yeah, point being that, long story short, yeah, cell potential and standard reduction potentials are state functions. Is it safe to say that elements that form negative ions tend to have very positive electrochemical potentials? Yeah, I think that's fairly safe to say. If a substance tends to form, if an element tends to form negative ions, like bromine, chlorine, fluorine, they all tend to form negatively charged anions, bromide, chloride, and fluoride. Those also do have largely positive reduction potentials. Again, we think of a positive reduction potential as being favorable in terms of overall cell potential. So yeah, those I would say there's a general correspondence or a general trend there, which I say is safe to make. Now there's going to be exceptions, but for the most part that's the case. Just a couple other questions here. What do you mean by higher in terms of the cell? I mean higher electrochemical potential. So it's like going uphill, like literally going up a hill. We recognize that if I have an object, like a ball at the top of a hill, where would that ball rather be is it will tend to roll downhill. Electrons are the exact opposite. They tend to roll uphill. They tend to roll up in terms of their electrochemical potential, in terms of their reduction potentials. That's where electrons like to go. So if I have a metal that's at the bottom of my table of standard reduction potentials, that metal will tend to donate electrons to a substance further higher up in the table of standard reduction potentials, because an electron going in that direction is going to a higher electrochemical potential or a higher voltage. For the standard reduction potential chart, does having a negative or positive value mean it can gain electrons more easily? A positive value means that the substance gains electrons more easily. So I kind of remind myself of that by noting that fluorine is always at the top of the table for the standard reduction potentials. Fluorine tends to gain 2 electrons and form the fluoride, should be a little space there, the fluoride ion. That is a very, very favorable interaction, and again, it's all the way at the top. I don't have that value memorized here, but it's at least 2 volts. That is a very, very favorable, very, very positive. So yeah, generally speaking, a positive standard reduction potential. Reduction is gaining. Highly positive standard reduction potential means that the substance very happily gains or accepts electrons. So I hope that clarifies that last point. Okay, so that's all the questions for today's lecture. If you have any other questions, please feel free to email me or stop by office hours and I'd be happy to discuss them. Have a good day, everybody.